All right. So hi, everyone. My name is Chris Follen. I currently work at F5, along with Nick and Oscar, who's here, and a bunch of other folks on the Wasm team. And I am going to be talking today about ahead-of-time compilation performance for ahead-of-time compilation of JavaScript to WebAssembly and improving the performance of JavaScript in that way. I'm calling this episode 2 Return of the Compiler. Some of you who were at Wasm Research Day 2 years ago or PLDI last year would remember the work that I did that is more or less equivalent to a baseline compiler. It was called Weevil, the partial evaluator. This is kind of an enhancement on that. It's turning that up to 11 and doing a lot more optimization and getting, I think, pretty good performance. So first of all, you might wonder, why JavaScript in WebAssembly? Like, why not just use V8 or SpiderMonkey or any other JavaScript engine? Well, so the use case for this kind of thing is in like function as a service or kind of data plane or embedded type environments. So at F5, we are running WebAssembly in a network data plane. Other folks run it in edge compute in the cloud. And these are what I'll call Wasm first use cases, right? So these only accept Wasm modules as a unit of execution for user code and not JavaScript or other languages. And this is for a number of reasons, right? So customers want JavaScript and we don't give it to them directly. So why can't we just use V8 or SpiderMonkey at the top level? The main reason is that we just simply can't accept minting of new code at runtime. Right, so there are a lot of security implications as soon as you allow emprtext to make new pages executable. That's heavily audited. Anyone can look at the CVE record of V8 or SpiderMonkey or JSC or any of the other engines. And despite people trying really hard and having great intentions, it is just hard to get this sort of thing right. And so there are a lot of bugs there. And if it's at the top level in your process, in your data plane, then that's not going to be acceptable. There's also a latency concern, right? So like a JIT fundamentally is just in time. It's in the name. So compilation happens during execution. And we can't really accept a compilation latency pause in the middle of, say, processing packets at 400 gigabits a second or something like that. And then kind of along with that, but a little bit distinct, is deterministic performance, right? So you want to be able to say that the customer uploads new code, that code has to run at the expected performance from the moment that it's activated, right? So we can't have this sort of latency spike where we say, new version of JavaScript, we're now interpreting until we get to JIT up, tier up, 10 milliseconds later or whatever. And then also there are kind of nice, more control plane management type reasons for this kind of thing. So, a Wasm module or a component is this like really self-contained unit of code. It declares its interfaces. If we just support this one thing, then we can support many different languages, and we don't have to do this kind of N by M integration slog where we say, okay, we have V8 or SpiderMonkey at the top level, and we have a separate set of host calls just for that JavaScript. And also, finally, bring your own engine allows much easier in-field upgrades, right? So rather than saying the entire platform is on, SpiderMonkey 148 or whatever, the user can say, hey, a new version was just released. I can upgrade my toolchain. I can rebuild my code, and I can just go ahead and run that new version right away. So there are a whole bunch of advantages to saying the engine is within the Wasm module. And so that, for various reasons, my past two employers and many others have chosen to do it this way. But it does mean that performance is not great. So before Wasm Research Day in 2024, we took an approach that I'll call interpreter in a box, right? So this is sort of the canonical thing that many folks do for many different languages, where you essentially take the portable interpreter that most dynamic languages start out with, for Ruby, for Python, for JavaScript, for Perl, whatever, and it's just plain old ANSI C or whatever, and you compile it to Wasm and it runs. And maybe there's a little bit of weirdness with like exceptions for set jump, long jump, or whatever, but pretty much that, most interpreters are pretty portable and that just works. The downside of this is that the performance is on the order, for JavaScript at least, is on the order of like 30x slower, at least when running on Wasmtime with SpiderMonkey as compared to the same SpiderMonkey version running natively. And that's on average. It can range up to 100x. It depends what the benchmark is doing. And there are kind of two reasons for that. The one obvious one is it's an interpreter. It's not doing JIT. But also actually interpreters on Wasm specifically are uniquely bad because of the CFI, right? Bird table instruction is not great as compared to the tricks you can do with native code. And so this substantially changes the kind of workloads for which JavaScript is even feasible, right? You probably wouldn't reach for it if you want to do some sort of deep packet inspection hook in your network data plane, right? Like that would be not reasonable. Okay, so 2 years ago, I introduced this tool called Weevil, which is a WebAssembly partial evaluator. And in parallel with that, wrote a new tier that's now upstreamed into SpiderMonkey called the Portable Baseline Interpreter. So I gave a talk about this, also a PLDI paper. But the gist of this is that it compiles JavaScript equivalent to what a native baseline compiler does. So it still doesn't require types. I'll talk in a second exactly sort of like what I mean by baseline compilation and why you don't require types. So it can be fully ahead of time. And this got some nice speedups. Basically, it removes the dispatch overhead from the interpreter loop, but you still fundamentally have a lot of like late bound dynamic behavior. And so it's still on the order of like 20x slower than native JavaScript chips. So where does the time go? So let's recap like what I mean by baseline level compilation. So and I'll be SpiderMonkey specific here because it's the engine I have experience with, but my understanding is all the engines work more or less the same at this level. So basically what happens is you'll start with JavaScript source, you'll parse it to some bytecode or IR representation that's pretty much one-to-one with the JavaScript source. So the semantics of the operators are more or less what the JavaScript operators are. And so that includes things like ad hoc polymorphism, right? So the plus operator can do integer add or string concatenation. You have properties and all the prototype semantics of JavaScript. You have all the proxy objects and hooks and everything else you can do that's very crazy is all in the semantics of that bytecode. And then to execute it quickly, what you do is you have what are called inline caches, right? So at every operator site, that could have some sort of pluggable behavior or behavior that differs based on types or the heap graph of the program. You have this basically function pointer plus data slot, right? And so initially that points to a very generic implementation of that operator that has all of the branches and says, I could implement it this way or that way. It could be string concat, it could be integer add. But then as you see the different types, the actual cases that happen at runtime, you will attach new what are called inline cache stubs that are specialized code just for that case. And the form is always check the conditions, and if the conditions still hold, then do the fast thing, right? And so basically you're memoizing here. You're seeing the behavior and you're generating code at runtime to plug in this fast behavior. So I say generate code at runtime because that's how SpiderMonkey works in practice on native systems, but actually it doesn't have to be. And so one of the contributions of my past work and the portable baseline interpreter is that you can sort of enumerate all the possible IC stub codes at compile time or over a corpus of code, and you can just generate them and have them in the image. So the actual like late binding, the actual dynamic pluggability of ICs, attaching a new IC stub, is just writing in a function pointer to a table, pointing to a function that already exists, right, that you knew ahead of time. And so that's why you can do baseline level compilation without knowing types. And that's, again, what gives you like a 2 to 3x speed up. What can't baseline compilation achieve? So why doesn't this get us all the way to where JavaScript jits are today? Well, basically what you can't do is you can't have inline operator flow, right? So you can't say, I have a group of operators together and I can optimize all of their behaviors together in a type unboxed way. And this is even worse in Wasm because all of the ICs become function pointer calls, indirect calls, and so call indirect has all of the checks that we know about. Right, and also you can't do unboxed operation, right? So basically, because all of the individual operators are individually pluggable, you need a shared representation, a common representation for the state of the VM at each program point. And so basically, if you have an operator like, let's say, an integer add, it needs to rebox that integer into a generic JavaScript value, a tag, a nan box or tag value. And then the next operator, let's say it's a subtract or a multiply, we'll do all the checks on that again to say, well, is it still an integer? I don't know. It was an integer 5 instructions ago. It might not be now. Well, it is, it turns out, and so you'll unbox it again and do the operation and then rebox it. And so what you think should be, just a straight line sequence of operations for like dense numeric code or something turns into, 2 loads for the 2 operands off the JavaScript stack, which is also needed for GC routing reasons, and then a call indirect to the IC, and then 2 guards and unboxes, which each are a compare and branch, and then like an and to mask out bits. And then you have really little tiny right there. You have the actual operation, an I32 add. And then you box it up, and then you return, and then you store that value back to the JavaScript stack, right? So this is why we're still like 10 to 20x off of native, because if you have an optimizing JIT like V8 or SpiderMonkey, you really do, if it understands the types and you have the right guards on the outside, you really do have just that I32 add, right? And if you wrote this code in like Rust or something or C, you really would just have the I32 add. right? So that makes me sad as someone who likes things to go fast. And so you know, let's think a little bit about what we could do. If you think about this, I think it really is kind of fundamental unless you know the types ahead of time, right? So you need somehow to know that I'm going to have a case where I have actual integers flowing through this code, and so I really can just do the i32 add, because the boundary of the system, like the VM that invokes me and like all the heap objects that have the values, are all giving me tagged, dynamically typed tagged values that could be anything, and so you really need to like break through that barrier to do better. So how do native JS engines do better? Well, the JIT hypothesis, the reason that JITs work at all, this is going back all the way to like, you know, the IC work with self and you know, the small talk optimizations in the 80s, is that behavior in most programs is like monotyped, monomorphic, right? So like once warmed up, once stable, you'll pretty much just be able to use your observations and specialize on them, and things will work. And of course, there are actual like polymorphic or megamorphic sites. You know, you actually have dynamic dispatch to like 4 different classes or whatever, and so the production engines need to handle that as well and not like re-specialize over and over. But pretty much like the idea is just observe what happens, specialize for it, and generate code. And so that's more or less what you do. SpiderMonkey takes kind of a nicely structured take on this, which I think the other engines are a little bit different, but like the overall concept is the same. What SpiderMonkey does is it actually generates the ICs and then just inlines them. So that's what WarpMonkey did like 6 years ago, and hoists the guards and remove the box-on-box pairs. So you might ask, well, could we do some sort of analysis to like just derive what the type should be from knowing, you know, something about the program, knowing the operator semantics, knowing the data? You know, in the simple case, if I have like 1 plus 2, you know, constants and a plus operator, I as a human can look at that and say, well, that should be 3, rather, so I know the constant, but I also know the type. But in general, you know, this kind of still needs a seed from like some initial state that is from runtime, right? So Hackett and Guo had this paper in TLDI 2012 that did the type inference system that used to be in SpiderMonkey and has since been deleted once WarpMonkey was put in. And the idea is that they had an analysis result that's a summary of what has happened so far, right? So it still fundamentally relies on the JIT hypothesis if I get to observe and warm up based on it. And then let me do a bunch of analysis and find the downstream implications and then specialize code based on that and have tripwires that invalidate code if that assumption breaks, right? So it doesn't say anything about the future, it only talks about the past. And so that's kind of what's there. So what we want is something that's fundamentally different, right? We want to know what the types will be without ever running the code. And if we can do that, then we can just generate the right code and we'll be good. So why can't we profile the code, right? This is the other question that comes up frequently, and including in context specific to Weevil. Why can't we profile and then see what the ICs are and then inline like WarpMonkey does? One of the problems is that we may not be able to run the production workload in a development environment. And there are multiple reasons for this, right? Like maybe we don't have all the same APIs, maybe we don't have all the endpoints, maybe we don't have production data sets. Like everyone likes to think that you have a perfect integration test environment that you can run on your laptop that represents your entire company's network, but of course that's not always the case. And so that's kind of just a really high bar to set for someone with your developer tools to say, you must be able to have tests that actually run and exercise all of the same code paths so that we can profile so that you can get acceptable performance. Like it's the same reason that not many people do like PGO or LTO, right? Unless they're a very well-organized and well-resourced company. Maybe you have a control plane do it automatically, right? So this is, Luke's cloud PGO idea. I've heard various people like bounce this idea around. I think that's super cool. I think that like that should be done wherever it's possible. The problem is that there's this thing called Conway's Law, right? So this is where the industry bias of my position here comes in, which is that you ship your org chart, right? And so I'm on a toolchain team, and that's a control plane problem. And so I say that somewhat glibly, but like actually what that means is that you need to coordinate with the other folks who are taking the thing that you're building, the tool, and embedding it into other environments. And you need to actually build the mechanism. So that's real human labor to build the mechanism to collect the information and aggregate it and feed it back and do the recompilation. And so that's kind of also a hard sell to say, well, we can support JavaScript, but only if you do this. There's also still the warm-up problem. So this doesn't solve the warm-up problem. You might say, well, you could use a profile for an old version of a code, and then when a new version of the code comes in, maybe it almost aligns, and we can kind of get most of the types out of that. that may not always work, especially if there's a whole new code module that's been introduced. Also, it's hard to manage. Or you have like a traffic mirroring approach that like tries to warm it up in parallel, and then once it's fast enough, then you switch over, right? But so all of this is much more complex than just saying, I have a compiler that can generate fast code, end of story, right? Okay, so why do we actually need interprocedural type inference, right? Let's actually look at some code here. This is very simple JavaScript. This is, what someone might write in a little like physics benchmark or something. You have a vector, it has an add function. Each element of the vector is pairwise added. And this is the classical JavaScript OOP pattern, right? So this is before ES5 classes or whatever they are. You would set up the methods on the prototype as just functions. And then we have some main that creates some vectors and adds them. So what do we actually need to do to see that this plus is not polymorphic, but is like an add of two integers or two floats? So first we need to do a global lookup, right? When we compile this function main, we see this new vector. This will be compiled into like a get gname op or something like that, right? So like it does a lookup on the global this, and probably if we have the global environment and we're analyzing the entire program, we can say it's probably this vector, which would have been a function up here somewhere, but it could be monkey patched sometime at runtime, right? Like there's nothing stopping the user from like editing the environment later. So already there's something that we have to analyze that monkey patching doesn't happen. Okay, and then we do a property access v1.add. So what does this mean? So this is actually, it looks like just a method call, right? Like to humanize, but this is actually two operators. This is a property read to get the v1.add, and then that's a function value, and then you call it. And so this lookup involves property access, which involves looking at the object shapes, which involves going through the prototype chain, because it's not actually this v1, it's v1's prototype. And then that prototype came from the constructor.prototype, which is different from the double under proto. And what it comes from, but is different from, right? It's a different slot. And so you need to like have all those semantics modeled. And then you need to devirtualize. So we only have one possible value. This prototype might not have been, or should not have been edited at runtime. And so then we can see, okay, this call is a direct call to that thing over there. So then we can propagate interprocedurally the types of 1, 2, 3, 4, 5, 6 through into the fields. And then we have the same property access stuff to look at the slots. And finally, eventually, we get to see that this is an I32 plus I32. But we needed all of this stuff, and we needed a closed world assumption, and we needed whole program analysis to see that no one mucked with like the global vector name, and no one mucked with the prototype object, and everything was still what we expected it to be naively as humans who don't expect unexpected things. So we need all those things just to get a fast add. Has this been done before? Has anyone tried to like boil the ocean here and actually build such a static analysis? Yeah, there are a few lines of work. So IBM Walla is like this analysis framework that comes out of IBM TJ Watson. This is like 2011, 2012. There's another line of work, type analysis for JavaScript, TAJS, which was like SAS 2009, and it's a group from Aarhus in Denmark. And so folks do this. The key idea is that you start with an Anderson points to analysis, a May analysis. Basically has points to sets for heap abstractions at like every storage cell in the program. You do abstract interpretation, so AI good kind, through the operator semantics. And you have to be really conservative in a lot of ways, right? So you have to, like if you read from an object, because this is a May analysis, you don't know if the field is actually set or not. So whatever .x could be .x on that heap object, or it could be on any of the prototype objects up the chain. So you have to meet them all in the lattice. And then all the fallback paths, like if it's a string, then it could call toString, and that could do a bunch of other stuff, and that could be .toString on object. And yeah, so it's extraordinarily bad in multiple ways. One of the ways that it's bad is that it's very unscalable, right? So they're targeting this world where you run this thing in CI or overnight or whatever for code scanning to look for bugs, and you have like minutes or hours runtimes. And you can see how bad it is if you look at like what TAJS requires for its storage model. Its lattice, its analysis lattice, is a flow-sensitive image of the entire heap at every program point, right? And so you can say, oh, we do sharing, we do persistent immutable data structures. It's still horrific. It's still really, really bad. Right, and so then the other problem with this is that it's just really, really imprecise, and I'll get to some examples of how that happens in a second. So what do we have? We have a native JIT approach to get fast JavaScript. It's got the runtime perf. That's what everyone runs on their laptops right now, right? Like that's great. That's in production. $1 billion thrown at it, it works. It does need warm-up. That's just one downside, but it is scalable to large programs, millions of lines of JavaScript. We have baseline AOT. It gets mid-level performance. It does not need warm-up. As we've shown, we can do the compilation without knowing types, so that's great. That actually fits our requirements, and it is scalable to large programs. So that's the reason we're on this road today. And then we have full program AOT analysis. It can get the runtime performance, actually. I'll give you one number later. I actually built this, and it does get performance in cases where it completes. It does not need warm-up, so that's great. It is absolutely not scalable to large programs. The one program I got it to run on was 300 lines of code. Anything more than that boomed on my 128 gigabyte RAM workstation. Okay, and then maybe there's some other approach, hypothetically, that gets all of our requirements, right? We get the perf, we don't need warm-up, and it's scalable. So we'll see. Okay, so I made an earnest attempt at actually building something like TJS or Walla or whatever with a lot of the same ideas. I called it Sparta. A great name, so I had to build it. Sound partial analysis for recovery of type abstractions. And so basically, it's what I mentioned above, minus the flow sensitivity, minus call site sensitivity. And there's some other tricks for like polymorphism, ad hoc polymorphisms and stuff. Like, talk more about it if someone's curious. It does work. On one benchmark, which is Richard's, which is an Octane, which is 300 some lines of code. Waiting for this to catch up. There we go. So to give you some numbers on Octane, the numbers are higher is better. They're an arbitrary unit of speed. The Wasm interpreter is 340 on my machine. With Weevil, I got about 1,000, so that's about a 3x speed up. With Sparta, 17,000. And as a ceiling, the native jet, SpiderMonkey jet on my machine, 28,000. So that's pretty good. That's like within 2x of native, right? And if you take the Wasm penalty on C or Rust is like 1.5 or 2x, that's like maybe almost as good. And in fact, if you looked at the code, it didn't have any guards anywhere because it was fully statically proven, just raw loads from essentially structs. So that's super cool. But then, I was like, okay, well, how good is this really? Let me take the next JavaScript file in my directory. Mandrill is 350,000 lines of code, and yeah, it ooms. So that isn't gonna work. Yeah, so the first insight that I had was we're not gonna be able to make a sound thing work. Like, we're not gonna be able to prove that the types are gonna line up. It's fundamentally not possible. That's a research problem. Many people have tried. I had to try myself to convince myself because I'm stubborn. But basically, we're going to have to be unsound or optimistic. And the reason that this can work is that we can use dynamic guards, right? So the idea here is that we shouldn't try so hard to say from first principles, I have a model for prototypes, for property accesses, for the entirety of JavaScript semantics, just to know that this means there's an add method. I should just be able to look at it and say there's an add method. And I should assume that nothing weird is going on. You're not going to monkey patch the prototypes later. And then maybe I'll have some guards to make sure that's actually the case, right? So we lose too much assuming that monkey patches could happen. So instead, let's have this general idea of building what I'm calling a likely types analysis. And it'll start with some pattern match syntactic notions of this prototype style class thing, as well as eliding a bunch of other uncommon behaviors. Let's just assume proxy objects with getters and setters don't happen. Let's just assume that I32 overflow to double doesn't happen, and go from there. And then add guards to catch the unsound sort of edges of that. The second insight that I had was that we worked really, really hard to try to get the class structure or the prototype structure so that we can devirtualize method calls. And AI good kind, so abstract interpretation, can derive a whole bunch of facts about a program, but not all. And the problem is that JavaScript programmers are extremely clever, right? So basically, if you have arbitrary execution to set up your prototype graph or your class structure with all the reflection opportunities that JavaScript has, you'll quickly get into a place where you can't abstract interpret your way through that arbitrary execution. So there's this thing called Rice's theorem, which is basically undecidability, but mirrored into the analysis domain, right? So you can't know everything with perfect precision about every program. So as an example of how JS programmers are really clever, in Box2D, which is another Octane benchmark, there's this really insidious framework that they build for their own kind of ad hoc class inheritance. Function inherit uses a single global singleton function K and rewrites the prototype slot on it to someone else's prototype. and then sets a third person's prototype to new of that, and then like overwrites the dot constructor on that new prototype object. So if you analyze this in a flow and sensitive way, you're going to get points to sets that have like every class in the program, and then every class has every property pointing to every other object, and it's just really, really bad, right? So this is kind of why TAJS did the flow sensitive stuff. You know, every program point gets its own copy of the heap because that's the only way you can see through that. Okay, and then as another example of how JS gets weird, let's say that we have something that indexes with, let's say that this index is a string into some anonymous JS object with properties A, B, and C, right? And you actually see this a lot in the wild and frameworks that are like copying over properties from one thing to another, setting up prototypes, whatever. So you might naively think if I see a get elem, which is this operator here, I can get the points to set as just meeting over all the fields, right? Because it could be any of them. I don't know what index is. Well, actually, it's not. It's that. So this double under proto double under is the prototype of this object. And this is the case because the JavaScript folks thought that this was a good idea, right? So if you use a key that is literally the string double under proto double under, you get the prototype object, which is a different slot from all the other slots. It turns out that it doesn't even have to be, I mean, obviously once you see it's a string, it doesn't even have to be literal. It could be like any arbitrary computation that produces that string. And so if you combine that with the previous thing I just showed, and you don't have flow sensitivity, you actually end up getting every object in every type set, which gives you this like cubic analysis that just explodes, right? So do we need a definitely not proto analysis, like a Boolean property that says this is not the string proto? Well, obviously we can't because halting problem. But like, you know, this is madness. No, this is Sparta. Okay. So sort of combining with this like prior insight of like, let's just chop off the hard edges of JavaScript. What I decided once, so that was actually my breaking point for the sound direction. And what I realized is that we could just like ignore meet over protos, right? So that's another example of something that if we understand classes or these likely classes as a first class thing and devirtualize through those with guards, then we can just ignore prototype objects. Seems to work. Okay, the last thing is, so I still need a points to analysis because I still need to know the types of values that come from fields. So like really quick from first principles, why is this important? If I don't see the value of things that come from the heap, or if I don't track the types of fields on objects in the heap, then essentially the only kind of type inference I can do is local, like within a function, right? Because almost everything that goes a long distance through a program does not flow as like a local and then an arg and then a return and whatever. It's going to be stored at some point to a property in the heap and then loaded back out, right? This is just the way that we build encapsulated programs. And so we need a points to analysis to say that we have a type set on different abstractions for different objects in the heap to give us the types of those fields. So there are kind of two classic answers to this. There's this design space. One of them is Steensgaard. This is 96, I think, or 94 or something. That is union-find-based. So the idea here is that whenever like any two storage locations in the program may be related, may connect, right? I load from both of them and merge the value together later. I'm just going to union them together. If they ever touch, then they're the same thing. And this is obviously very conservative, but it is sound. And then the other end of the spectrum is what's called Anderson points to. The idea here is that we have a set. For every storage slot in the program, we say it could be one of these like 17 different things. And if something from this set or this location flows into that location, there's an inclusion relation, but the thing it flows into might still be bigger, right? And so what this does is at merge points, you retain more precision because you don't like have the collapse flow backward, right? So it's kind of a backflow prevention thing, but the cost of that is that you have these really big type sets. So Steensgaard is almost linear, right? It's like Ackermann function of n or whatever because of the union find, but very coarse. So any interaction between any two things collapses everything. If you try to use this in your program, it basically is just gonna like give you no types at all. So it's typically best suited for like a lower level compiler where you're trying to do like opportunistic code motion or opportunistic alias, resolution with code placement, and not for like a picture of the whole program's types. Anderson is much more precise, but it's really, really bad in terms of runtime and memory. So ideally, we'd want the precision of that, but we want to maintain class identities, right? So so sort of the insight that I had was we usually can't do anything with greater than one points to set member anyway, but we still want to keep the precision without the backflow. And so maybe we kind of do both. So I'll skip ahead a little bit here. This is a new, as far as I know, I haven't seen this before. This might be novel. A new kind of hybrid between Steensgaard and Anderson, where there's a 3-level hierarchy. So we have these allocation sites, and these are essentially the Anderson points to, like every program point is one of these. We group these together into the classes. So these are the classes that are either literally the ES class or the like syntactically derived likely class. That's the the function with a prototype object attached. And then these, whenever they meet, so whenever allocation sites or classes meet, then we union together. And so this looks like a lattice, but actually it's a tree. So a tree is a kind of lattice, right? It's actually a tree because if two things ever union together, then like that becomes one node here, and so you can't ever have crossing. And so this is actually really, really nice because it gives you this this 3-level thing, and you can actually attach types to all 3 levels. You have precision at whatever level you're able to derive. So you have precision for exactly the allocation site if that distinguishes things, and that's useful for like raw objects that don't have classes. And then you have precision based on classes, and you have that natural collapse. So if you have like multiple constructors, you kind of want that collapse. And then you still have the fallback of the unions before you get to any objects. You still have some types. Okay, so what do? We perform AI on function bodies with hybrid points to with this lattice. We devirtualize. This builds the call graph at the same time. This is whole program. We seed it with these likely classes, and we ignore prototypes. And then we, how do we actually consume these types? So, okay, what can we actually do with these, right? So it's a likely types analysis. We don't actually know that the answer is sound. And so we could use these types as sort of heuristic hints for fast paths that we could generate, right? So like, oh, this field might be in int32, so I'm going to have a branch and say, if it is int32, I go do the thing. Otherwise, I have the generic path. But that's actually not going to bias that much. All that really biases is code size, right? Because we could always generate the branch and the specialization for every type. And so really what we want to do is we want to share the cost of the guards. And so the key idea here is it turns out in a 32-bit platform, there is a free 32-bit word in SpiderMonkey's objects. So I saw those 32 bits that were all 0, and I was like, I want to use those bits. And so what we do is we stamp the objects with an ID that corresponds to that lattice, so specifically the allocation site in that lattice. There's also a bit I steal at the top that says the types of all the fields in this object correspond to the likely types that this analysis derived. So we have the constructor. At the end of the constructor, we actually validate all the type tags dynamically, set the bit, so we stamp the object. And then what we can do is at the start of a function, when we get a rest to any object, we can have just a single guard that says, is it class 23? And are the types still valid? Yes. If so, I can do raw loads from the fields without any dynamic type guards. And I know that it's going to be an int32 dynamically. And so the trade-off here is that at stores, we need to actually invalidate that bit if it's not. But we know statically what it should be because we know the class, right? Because we know the types that flow through. Okay, and then the tree structure, I won't go into too many details here, but the tree structure actually plays nice here because if we do it in DFS order, we can like have range checks as well as individual checks, which is super nice. Okay, and then also I won't get into, there are actually 2 kinds of predictions. There's type and slot. So if we know that this thing is the third property set, it's going to be in slot 3 in the object. We actually want to have a raw load that's guarded that loads from that static offset rather than do an IC lookup or something. So that's another dimension that we do here too. How are we doing on time, Ben? 3:24.
I think you have 15 minutes.
Awesome. Okay, I have time. Okay, so what do we do with this now? So we have types, and they're likely true. We're not going to guarantee that, but they're likely true. So we want to consume them and actually generate code, right? So again, because they're not necessarily guaranteed, we still need the generic path. So I initially experimented with something. So there's this paper in like 2018 or something called static basic block versioning. So I initially experimented with this, and the idea is that you parameterize all your code gen on tuple of block and type context. And so that type context includes like all of your locals or SSA values or whatever. This one's an I32, that one's an F64. And so what you do then is if you have a type branch and you're testing, is this an I32 or an F64, you branch to the appropriate context of the successor block. And so this will give you code that's like, if you just look at the path that's actually executed, that's perfect, right? The problem is that you have combinatorially many possibilities. So imagine you have 10 locals, all of them could be I32 or F64. If you just statically try to enumerate all possibilities, you're going to have 1,024, 2 to the 10 possibilities where they're each I32 or F64. So this quickly blows up. So the paper itself obviously is not that naive. They have a bunch of heuristics to basically budget and try to like have coalescing of versions. So they have this theta function that merges together similar versions, some widening or collapsing. But it still blows up in practice, or at least I couldn't get it to be that stable. And so the basic idea that I landed on was, let's have one optimistic path and one slow path, right? So if we're going to pay for the cost of an analysis that says these types are likely these types, let's code-gen a body for those types, and then let's code-gen just one completely generic path. And so we still do the type context thing. We track assumptions, so dominating guards, known types, and we track that through we actually do a fixed point pass first to find that for every program point in every version. And then we go back and do code-gen on top of that. Yeah, basically every branch on a type or on some condition that goes into the type context splits the type context. Yeah, there's a lot of careful sort of engineering here where interesting decisions around, okay, if I diverge a little bit, sometimes it's better to have on the cold path. So, say an I32 plus I32 actually overflowed to a double, right? Which is allowed in JavaScript. Maybe you want to like have a check and try to reconcile and then merge back in. Or maybe you just say, okay, you're on the generic path forever. And there's a trade-off there, because if you merge it back in, you sort of degrade the most optimistic path for everyone. You remove that assumption for everything downstream. But for the path that did follow that cold path, it ends up still being a win. So in most cases, it doesn't make sense to do that, but there's a lot of very careful like A/B testing you have to do to get those heuristics right. Okay, one other thing I'll say here. I won't go through all the details, but irreducible control flow ends up happening a lot if you have block versioning, because you can imagine if you have like a loop nest and you have your nice structured reducible control flow out of JavaScript, and then in the middle of the loop you go from the optimized version to the fallback version. That's a side entrance to a loop. That's not good. And so this whole thing I wrote with Waffle, which is the same SSAIR library I wrote for Weevil. Waffle has what I call the reducifier, that does sort of the dual to what relooper does. So relooper adds like a label and then does a bird table at the start. The reducifier just duplicates code, duplicates the tail. And so this, again, this is one of several reasons I discovered. And so I actually had to add some cleverness in my loop context, or my type context, where I denote which loop headers I've passed, and then I sort of have like a second version, and I tail merge, and it's really gnarly. And I just want multi-loop, please. So that's my one ask for the CG. Yeah, great. Thank you, Conrad. So maybe I'll see if I can champion that. I don't know. We'll see. But it seems like it was always like needed evidence for like this is actually necessary. So this is actually necessary. Okay, so I needed a name. Every project needs a name. I couldn't use Sparta because it's not sound anymore. Jaeger monkey, iron monkey, warp monkey, whatever. I need a monkey. It turns out there's a monkey actually called the night monkey. Night is non-local inference with guiding heuristics for types. Okay, the coolest thing ever. So I looked this up on Wikipedia. That's a night monkey. There we go. This is a screenshot from Wikipedia. The Latin genus of a night monkey is Aotus. So it's an AOT compiler. That's super cool. Super cool. It was made to be. Okay, so these are the results from night monkey. So I'm showing some columns here. This is Octane, except for the last one, React Bench, is React, the UI framework, doing server-side rendering. Higher is better for all of the rows except for the React Bench, where lower is better because that's milliseconds per render. And so the columns are Wasm interp, that's SpiderMonkey just running on Wasmtime. And then Weevil plus Pebble, that's what I published last year. That's the baseline level compilation, again on Wasmtime. And then AOT is this work, Night Monkey. And then native JIT is a ceiling. So that's same version of SpiderMonkey, but compiled and running on the native machine that I'm doing these tests on. And so some of these numbers are really good. So Richards is like a nice one to optimize, and I stared at this a lot. We get like 3x from the Wasm interp to like Weevil plus Pebble, which is last year's work. We get about, I think this is like 28x or something with AOT. And then that's within about 3x of native JIT, right? So that's So if you remember the numbers from Sparta, the sound thing, I got 17,000 with Sparta. So that's not quite as good because of the dynamic guards. But I would say that's still pretty good, right? Like if I were writing a program and I were told I could use, rewrite it in Rust and be like right at the forefront of performance, or I could use my existing JavaScript and it's only like 2 or 3x slower, that's a pretty good trade-off compared to 30x slower. And so overall, I think these numbers, so this is like a 1.5 or 1.7x with Weeble Pebble, and then it's more like 7x to AOT, and we're within about 4x of native. So yeah, that's it. Okay, one last thing. How do you actually test something like this? Well, how do you build it? How do you glue it onto the existing engine, and then how do you test it? So I wrote this as sort of a clean new compiler from the JS bytecode backward. So I had this, so I used to be on the SpiderMonkey team, and I would love to get this upstream, but I know them, and I know they would run screaming from a lot of this, and so I'm just kind of assuming for now this is going to be on a fork until it's proven and widely used or whatever, if it is. And so I figured the more maintainable thing here was to have a clean interface, so that's the JS bytecode, and new compiler from there back. And it's written explicitly to be portable and to be able to run inside the Wasm module or outside. And so when inside, then you generate the Wasm bytecode, and I'll tell you in just a second what we do with it. When outside, we actually assume the presence of Wiser, so this is Nick's snapshotting tool, and we read out from the heap snapshot in the Wasm module the same JS source objects, and because we know their layout, because the versions are locked together, and we actually interpret the data structures and do the same compilation. Okay, so how do we test this? So all of the test harness stuff for SpiderMonkey assumes that it's a JIT, because it's a JIT. So of course you just run the shell with the JS file and see if it passes. And so what I did was I actually wrote a runner that wraps Wasmtime and provides a host import that is essentially func.new. It's not func.new because we don't have func.new, but it's essentially func.new. And so when this runs inside the Wasm module, I can just create the new functions. I can instantiate them inside the current execution. I can plug in the function pointers, and I can run the tests. And so using this, I've run all of the JIT tests in SpiderMonkey, and they're all clean, no failures. And then if you don't want to run your compiler inside the Wasm module because that's probably slower, you can't use parallelism. Also, you'll dirty up your heap image with a lot of mallocs. Instead, you can run in this mode where you take the Wiser snapshot, you run the thing as a native CLI tool outside, and then that tool will append the new functions on and poke the function pointers into the heap image and rewrite the module. Okay, so that's that. Okay, one more thing. So there's this project that probably a lot of you have heard of if you've Googled around for how do I compile JavaScript to Wasm, which is POR4. And so I want to be very careful and also kind to this project because it is an extremely ambitious and very cool project. So what is POR4? POR4 is a compiler written from scratch to do AOT compilation of JavaScript to Wasm. They're currently at 62% of ES262 tests passing because, again, very ambitious project. And so their whole thing is use this if you want to write new code from scratch and you can understand the limits of the compiler. So I tried to get all of Octane and my React bench to run. I got just Richards to run. I gave the reasons why the rest didn't, and they all kind of have to do with missing, well, most of them have to do with missing pieces. There's some weirdness with closures. The compiler itself with Stack Overflow generated a single function that was 261 megabytes. So a bunch of stuff like that. It's again, clearly very ambitious and a very cool project, but it's not quite there. And I think that has more to do with the approach, right? We started with an existing engine and then said, okay, how can we add a new tier to it versus completely from scratch? On the one that it does run, Richards, this gets 1470. If you'll recall, the number that NightMonkey gets, AOT compilation, is about 10,000. And so the reason for that is that POR4 also does not do interprocedural type analysis. It assumes that if you want performance, again, because you're using this for new code from scratch, you'll add TypeScript type descriptions, which is actually probably the right answer. And actually, we should also do that in our project. But this doesn't work if you have a large body of existing legacy code, which is exactly what Octane is. Yeah, so here I just say all of that. What am I going to do? I'm going to clean it up and try to merge it into Starling Monkey, which is the Bytecode Alliance JSVM and runtime inside of Wasm and components built on top of SpiderMonkey. Continue to refine, maybe, ingest TypeScript ascriptions, right? So like right now, the analysis is like pretty good, but you probably also want a path for users who know what they're doing to say, oh, but I really, like it got it wrong here and I really want to make this particular part fast. So let me add some ascriptions to this particular part as well. So there's a nice progressive ramp there. And then who knows, maybe, there are other dynamic languages in the world and I can direct my efforts to another one next. We'll see. Yeah, that's all I have. Questions?
Very cool stuff. I'd like to understand the lattice that was actually a tree better. So yeah, could you just like briefly explain it again?
Yeah, so it's hybrid. So it's a points to lattice, analysis lattice, that is a hybrid of Anderson and Steensgaard. So the Anderson part is that we have a separate abstract value for every allocation site in the program. So that's these alloc nodes on the bottom. These will either belong to some likely class, which is this like prototype shaped thing, or they won't, and there's like an anonymous class for all the bare objects. And so that's what these represent, is each of these is a collection of allocation sites. Each allocation site is exactly one class, and so that's tree shaped. And then the union nodes are created as these meet each other in the analysis. So actually, I guess if we were to be really formal about this, this is like the power set of all unions, and then like we descend it based on, how would that work? Based on union find. But basically, yeah, so what actually happens is there's just a union find data structure. And so the like enum data type that represents this is union of one index into that. And we'll go off to the side table, the union find on the side, and like meet them if we see to. Yeah.
So you have, so the class row it's still a single type, but then you're collecting all the allocation sites for that type.
Yeah,
in
exactly.
Single thing. And then you're doing union find across types, so you have equivalence class. Oh, this is for the multiple constructors, so there was multiple ways to construct the same type.
Yeah. So the multiple constructor same type is all of the allocs going into one class. That's the insight there. And then the classes going into a union is essentially just I wanted a level that wasn't degrading all the way to any object. And so in most programs, you still have kind of this disjoint split of the heap where maybe I have like my polymorphic set of all my UI elements that go into a heterogeneous list. And so those will union together into a big clump. But I still, if I can, want to keep that separate from like some other object from some other part of my program.
So, okay, you've got like your collection of allocation sites that all allocate foos. So foo is a class of multiple allocation sites, and you got your bars, a bunch of allocation sites, and then you meet a foo and a bar, and you get one of these union things.
Yep.
But what do you know? Does it like, it only tells you anything if foo and bar happen to have the same type at the same field offset or something like that?
So there are two levels to this, I guess. There's the like just raw type inference, and then there's the like what do we store on it? What do we hang on it? So at each of these levels, on every alloc, on every class, and on every union, we have basically a dictionary from a field name, which is like an atom, to a typeset. And the typeset itself is like this lattice plus plus the power set of all the primitives. So just a bit set for the primitives. And so basically, concretely what happens is if I have a store and I have some value that I know is alloc n, I'll actually update the field typesets for, say, store to field x. I'll update the field typesets for field x on alloc n and class n and union n. And then when I read, if I know it's alloc n, I'll just read alloc n because I know that I wrote into it. And then, so.
Okay, yeah. So there's like some, propagation of information. So a single field could happen to be top, but another field might be like a specific type, and that's great. And
exactly.
In between. Okay.
Exactly.
Okay, thanks.
Are you using or are you considering using branch hinting for the like type checks and this kind of stuff?
I would love to. I was banging my head against a thing last night where I had, so I have a 32K iCache on my workstation per core, and I had 37K of hot code because of the version splitting. I would love nothing more than to say this block is cold. And my robot that was assisting me told me, well, you can just reorder the block. So no, you can't, because like my control flow reconstruction and Waffle will just like do the DFS regardless of the order, and then Crane Left also will do a DFS and like find the block order. So there's no way you can actually influence the order of the blocks in the compiled machine code. So I would love that.
Yes, second user of chain.
Yeah.
Are there other questions? I think this is super cool. I have a question. So what might be the takeaway for other languages? Do you have to build a custom thing for the next language that wants to do this technique?
Yeah, so there's an interesting interaction between my takeaway message here and the one that I had like 2 years ago, or with Weevil. With Weevil, my whole thing was, here's the partial evaluator. You just need your interpreter, and you can p-eval it, and you'll get a compiler for free, which is the Feudamore dream, right? And so it turns out that I think, so that's good. That will get you like a 2 to 3x speed up. That will remove your dispatch overhead. But I think to get further than that, you really need semantic knowledge of the language itself, right? So like an example of the kind of thing we do is the object stamping and guarding, right? You really just need to understand like the JavaScript object model to do that. And that's kind of hard to do in a generic way. So I think there will, to compete with the $1 billion that have been invested in JavaScript engines, on all the tricks, I think you need to do all the tricks, I guess.
On the other hand, if you do all these tricks for any other language that isn't JavaScript, your results will probably be really, really good.
Yeah, exactly. So yeah, I concretely, if I get time and management buy-in, I would like to do this for Python as well. So yeah, let's go down the list.
Great. Any other questions? Oh yeah.
You had many mentions of cubics and so I'm curious, how long does this take in terms of like running this past on these benchmarks and such?
Mandrill is the biggest one. 350K lines of code compiles in 5 seconds.
I don't know if you saw, but Wasmtime does support branch hinting nowadays.
We do.
So
cool.
If you add it to Waffle, then you can do that.
I even added the cold block support. I didn't realize it was wired through. Excellent.